Раз. Окей. Всем привет, я Евгений Пальтсев, и я хочу рассказать о том, как и зачем внутри Linux используется самомодифицирующийся код.
How, why, and where Linux is using self-modifying code in the kernel.
Я работаю в компании Synopsys,
I work at Synopsys company. The team supports open source code. I support Linux kernel and Synopsys and others like me focus in Linux kernel and UB drivers and platform support. That's what we have been doing. As to self-modifying code, I decided to look at it when I was looking at the names of those kernel. The section of the code or the kernel is marked as read-only, but actually it could change. So I would like to tell you about it. Our presentation will consist of two parts. In the first part, we'll take a look at different subsystems in Linux kernel to use self-modifying code. It will be an overview without in-depth analysis how we can implement those subsystems. First of all, it would be difficult to speak about everything in one presentation, and all those subsystems are using architecture-specific functions, so implementation of those functions will be different for different architectures. In the second part, we'll look into more deeply into implementation and why this implementation could be very unusual, non-trivial. That will be based on my experience of static branches implementation for ARC. We should start from a picture, a very nice picture. Here you are.
Итак, где в ядре Linux используется самомодифицирующийся код?
So, where do we use self-modifying code in Linux kernel? Kernel modules, that's what we think in the first place. Kernel modules, Linux kernel enables file system drivers and other components to be just loaded as modules to be, so we can upgrade the drives and extend the functionality of the kernel without the need to reboot the system. We modify both the kernel and we adapt external code and module code by load linking. We changed the kernel code and we also changed the code of the module uploaded. And we don't know initially the address upon which it will be loaded. Final link will be done by the kernel itself. The kernel will identify the addresses and offsets of its functions and variables used in the code of the module, and we'll be changing and modifying that in the course of the module. Our kernel module is not the only system which is using this self-modifying code. For example, we have to support this architecture. It's several architectures that they can rewrite ARC-specific code. How should we write the code? Some conditions should be added up. It's not the hardware with bugs. There could be different versions of the components, and we have to check it up to send it to hot parts of the code which are done repeatedly and whose productivity is critical for us. Some architectures for that use self-modifying code. They substitute some of their functions at the early stage of kernel initiation to avoid high overheads, and it does require very sophisticated implementation because we actually replace the functions which are not used by the kernel at this moment in time. We looked at several subsystems which use self-modifying code and which change the kernel code when it's not just at the execution stage. This is quite interesting, but it's even more interesting to look at those subsystems which can change the code which is executed right now. That's what we're going to do. You need to change the vulnerability in Linux kernel without rebooting the thousand servers. So you might add a live patch system. This way, live kernel patching could be done without system restart, and we can apply kernel-related security updates. It's not the only instrument which enables us to patch Linux kernel on the fly. But that is the first element we added up to the kernel. So live patch was based on key patch and key graft, which are very similar in their use. In point of fact, live patch does not use directly self-modifying code. Instead of that, it uses the mechanism of function substitution provided by other system, ftrace system. How does it happen? At the stage of assembling, the kernel has got more instrumentation. Special instruction is added at the beginning of each. It's a special instruction, NOP. It does nothing. It's like a plug, you know. Whenever it's necessary to substitute this or that function, this NOP instruction is substituted by ftrace subsystem call. After that, it will call the function which we updated.
Okay.
We needed kernel function interception. kprobe system is very good. It can intercept kernel functions and to add some custom processor for them. In those processes, you can compile information for debugging or collect information which is necessary to assess performance. How do we add this up, the developer? We use trap instruction. The kernel could substitute the instruction on the address switch for which we have to add this processor, and so it allows us to install pre-handlers and post-handlers for kernel instructions. And actually, it has got the change execution paths and collects performance, and so it could be function entry as well and function return. Great, we played around kprox, and maybe after that we'll have to debug the kernel. And KHDB can help with that. It can set breakpoints, it can check and modify data structures, memory and registers, and control kernel running flow. It's like GDB, but for the kernel. KGDB is the backend of the debug. It could be used with external GDB front-enders. It will be connected through a serial port or with internal KGB front-end. KGDB is rather judgmental technology because we use this code. It's questionable because we use kernel code to debug kernel code. But some features may modify kernel code, like breakpoints installation command. It can also use special trap instructions whenever it's necessary to install breakpoint. KGDB code substitutes the instruction and address where breakpoint should be installed, then we execute it. We generate hardware exclusion, and then it's sent to KGDB processor, similar to kprox, but in kprox case we have to process very rapidly, not to slow down the kernel work. In case of KGDB, we are not in a hurry, actually. It's rather interesting if there is a bug when we do the buffer and we rewrite the code of the kernel. Will it be self-modifying code or not? We're not sure. We started optimizing hot points in the kernel, and there are static branches. That way we can optimize branches in some conditions. When condition changes rarely, but the transition is in highly overloaded code, and branch itself is in hot code path. And I would like to try to figure out why implementation of self-modifying code could be quite trivial and unusual. I'll speak about architecture. Those implementations and examples will be based on static branches. Next version of the patches will be adopted with very small changes, perhaps real soon. On the slide, you can see that link on discussions. Actually, it's slightly outdated link. I already sent a new revision of the patch with the latest changes and upgrades, and I didn't receive any objections from the maintainer. I send it to. I hope that it's due to very high quality of my code, or maybe because I sent it only 1 hour ago. But I can hope that it's because I'm cool. Static branches were developed to optimize the code of inclusion and exclusion. Actually, it was used for trace points enabling, disabling, and we were checking up global variables for each trace point. This checkup is not very expensive, doesn't increase overheads, but it could be a problem because there are many trace points in the kernel. The optimization of the code for trace points actually brought us to creation of static branches, but then they were disseminated around the kernel, and they are used everywhere in dynamic print K code, in scheduler and memory management, network code, and many other points. That's where those trace points are used. Nowadays, in this kernel 5.3, actually there are lots of architectures which are supporting x86 and ARM, both versions, x86 and 84 as well, and others. The slide says that those static branches are supported by major architectures, but when I was showing this slide to my colleague, he said that, is it right to say so because static branches are supported in ARC, if we think that our architecture is not the main one, but I didn't correct the name of the slide. This colleague is not here in this room, so he will not go berserk with me for that, but this is not very important to make those changes because the time has come to support static branches and ARC architecture. It should be there. Initial idea of static branches was to speed up the kernel, but actually because we wanted to make maintainer happy and to simplify adoption of different features which otherwise could slow down the kernel for us. That's why they were discarded. Now, implementation, static branches. So here you can see the regular branch. We check out the conditions, then get onto this or that branch of the code, into one of those. In case of static branches, the major idea is that we should switch between branches of if statement by replacing branch instruction with NOP, or vice versa. If the conditions are changing, we rewrite it and switch to NOF instruction. We met this instruction when we're speaking about a submission of the function by X trace system. NOP instruction is good here as well. The replacement of the structures when we are shifting to NOC and back, we're switching between two branches of the code. That way we get rid of a certain number of instructions, and also we don't have anymore any delays of caches of data, and actually we avoid those bugs or shifting to the wrong branch. From the standpoint of user writing the code who would like to use static branches, adding static branches into the code will not require global changes in the code.
We won't have to use at least explicitly Ausländer and other specific functions. For instance, in the slide you can see the code of conditional expression and the corresponding expression using static branches. They look quite comparable. It is quite pleasant that if our architecture doesn't support static branches, or if it supports, but the support is switched off in this configuration, it will just be assembled and work not with static branches, but with common conditional expressions. If we want to optimize something to add static branches to the general code, you shouldn't be concerned that the assembly or the execution will fail. Everything will work, at least theoretically. In case of implementation of static branches for our architecture, we'll need to determine define one structure and to analyze the function. One of them changes branch instruction to p-reverse instruction. Two others realize the use of branch and NOPA instruction in the course of optimized conditional change. Not so much to be done. Thus, we have the instruction of branch and NOPA instruction, both of 32 bits. We have to be able to replace one instruction by another one. That should be done on an atomic way, because the code using that instruction, which you want to change, can be executed on the neighboring processor, or during the replacement there might be an interrupt, and the instructions that we're going to change, and we cannot allow that in the code, will be an invalid instruction. Otherwise, in addition to optimization, we'll add a bug to the code that's not what we wanted to implement. Similarly, the replacement of one instruction by another one doesn't look difficult. Let us write the new instruction at the address of the old one. Is that all? Not quite. Compiler can split 32-bit entries into several entries of smaller size, and we won't have to replace atomic instruction. There is a wonderful macros write once that made it possible to avoid splitting by compiler of the entry of large size into several entries of the small size, and that's what we need. We apply it. That's all. Not quite. We have caches, and for our audience, cache instruction doesn't support the equipment for coherence of cache data. We want to update the instruction. We write a new value of instruction. It is in cache data. We might have a copy of that value in cache instruction, and it will remain there until the line of cache instructions will not be replaced. We cannot really predict when it happens. Thus, we have linear conditional transition. We change the conditions now, and really they are changed, we don't know when, so we have to manually update that value in cache. What do we have to do for that? We have our updated values in cache data. We have to flash several lines of cache data in which our instruction lies, so that these lines of cache data will be to the lower level of the memory displays. In cache instruction, we have to mark this line as invalid to do away with the old copy of the instruction. So next time, well, you apply through the pipeline, that will you will go to the new instruction, we add the necessary code, done. Not quite. In 2019, in a China, there is a certain process. We have updated the value in cache instruction for the current core, but we haven't done it for other cores. So we have a funny situation. The code of our conditional change might be different depending on the core. It doesn't sound well. Thus, we'll have to add inter-batch interaction. We'll call the code of invalidation of the instruction at all the cores to remove old values of the instruction from the cache at all the cores. So we add. Is it all now? Not quite. It might happen that our instruction intersects the boundary of cache lines. That is a valid situation in all other instructions. In our case, that might interfere with the change of our instruction on an atomic level. So how can it happen? For instance, we have two processes, zero kernel and first kernel. To the left, you can see two cache lines of data cache on zero processor and the two cache line of cache instruction on the first processor. We need to update our conditional expression. We have a new instruction. We record it on on core 0. It gets into cache data. For instance, on core 1, we execute the code containing our static branch and our instruction. This instruction gets to the boundary of cache line. I haven't said that orange and green rectangles show our substituted instruction. Orange is old value and green is new. We have written new value on core 0. It gets into cache data. Then we flash a line of the cache data, and it gets in the instruction gets into the memory. The lower part of the slide on core 1, the code reached the place where our new instruction is given that we replace. Half of the instruction is here, and the processor adds the lacking cache line to cache instruction. Suddenly, we have half updated instruction. One half is old and the other half is new. We will be lucky if we get some invalid instruction which the processor would not be executed, and there will be an exception that we have an invalid instruction. Probably we'll have a good instruction. For instance, a branch with a different address of transition will execute it, and in reality the error will be shown up later, much later. This situation cannot be debugged, and it will be different even to repeat it. For instance, if we execute the instruction a bit earlier, in cache instruction we'll have the old value of the instruction, it will be known. If we execute it a bit later, will mark as invalid the instruction cache, and the new instruction will be added to cache, and that will be normal. But after we have learned about the problem, we try to correct it. For these persons in our functions arch, static branch and static branch jump, we have special condition for leveling the instructions so that they wouldn't intersect the boundary of cache line of the instructions which we had. This can be done using some certain directive of the assembler. That seems to be all, but not quite. Actually, we have to interrupt and think, what are we doing and what we are correcting. We started with a common entry of 32-bit value into the memory. Now we have manual cache imagine, interprocessor communication, special code alignment. And these are not all the problems that we can face. For instance, we might have circular dependencies. What can it be in our case? We want to optimize cache operation codes using static branches. We added static branches to the code, but static branches use the code of manual control of cache. So we have a circular cyclic dependence. If we don't process it, probably our code will not operate correctly. A special problem might be if you want to use static branches in early code. For instance, we want to add change the condition of static branch before the core under the system of static branches was initialized. If we don't process especially that condition, if we don't initialize static branch in the early code, we might have problems. Some problem might also be interaction between different self-modified code subsystems. For instance, we can use static branches in our model because the core processes the situation, everything will work. What will happen if we will use KDDB to replace the instruction? Probably that is not the best idea. So what is the outcome of it? The self-identifying, self-modifying code is a powerful tool that makes it possible to solve a very complex problems. We have analyzed the problems in the implementation of static branches that are beyond the layer of abstractions of realizations, implementation of the subsystem. Besides this being concealed, self-modified code requires a careful attitude because it might create complicated errors which are not easily revealed or debugged. So you should use it carefully and responsibly. Thank you. Any questions?
Итак, Andy, you are the first.
Спасибо за доклад.
Thank you very much for the presentation. I have many questions.
Не будет ли получаться так, что
might it not happen that due to this modification of caches, all our efforts
мы хотим увеличить
that we want to increase productivity will result in decreasing the productivity? You already mentioned debugging. That's a good question. That's why I have said that you have to use it carefully. Static branches are needed for optimization of such code where the conditions change really. For instance, we have some hardware feature which we check once, whether it is present or not. We have changed the condition one, and then in the whole code, in the hot part of the code, if that is a hardware key feature, we call the code that will process it. And we have changed the condition one time during the operation of the core, but if we are not using static branch but common branch, the check of the condition would follow each time in the final code if that will be a patch fault. If we replace any random branch by static branch, if we change everything by static branch, our productivity will be worse. No microphone. As to the macros, there is a special feature. Probably I won't give you an exact answer, but Linus had a small article concerning Keras macros, and he advised to remove them from everywhere because they didn't improve, they worsened, they lowered the productivity. Depending on how the developers used them, and in certain cases it was not possible to predict anything. He's not using the mic, I can't hear. In this case, this is not helpful. Yes. For instance, if we have some rare fault, hardware fault, it can be rejected. We might have a static branch that will be always switched on or switched off, either for variation of hardware will make everything worse or make everything better. Thank you for the presentation. I like the second part concerning the responsible use. I have a question concerning the first part when you discussed significant variability. A lot of mechanisms which we have, starting with core modules that can be classified as self-modifying code. You considered it from the viewpoint of security that some of these mechanisms will be used in runtime, production mode, and such as HDB. Probably they will be used for production, I hope. So from the viewpoint of safety, we think that KGDB will not be used in production, and it is interesting. We have been discussing live patching. Have you analyzed what of these will be needed in production mode? And what security people had to think about, we shouldn't close it. KGDB, in principle, we think it is closed for production. Kproxy in runtime. I can just imagine approximately. Was it for you? Was it interesting for you to analyze it? This is not related mainly to safety issues, but right now I can tell that we might use some modules or live patching. Kproxy, we are not using any special tracing for profiling. It can be switched off condition. KGB, we would like to switch it off. As to the variables that I mentioned, there is a great number of other tools that are also using self-modifying code. For instance, GPV, they have GIF in their core. That depends on the systems that we need. I can't tell you immediately. So we have to process it for the system for which it will be suitable. If we then we don't want to switch it. So I would like to note as to the users. Do they have any strong opinions as to what shouldn't be switched off so that security people would know about it and never switching off? And you mentioned live patching that we are not taking into account. But if you haven't realized it, that's okay, that's for general discussion. I will answer for Evgeniy. Evgeniy mentioned implementation of static branches so that we can collect the data that work on the two different configurations. Please do not switch on other. Evgeniy will be not happy. It is known how we can use it. As to the hot code, is it the same code that will launch processing exception mode, for instance, page fault? Can you use the mechanism of static branches there, or is it only for C code? There is no simple answer to that question. Generally, you can do it. For instance, I have seen in architecture x86 implementation of all these macroses as assembled macros. You can use static branches in assembler code. And as far as I remember, the same x-6 patches instructions are more complicated. They also, first they change the instruction, patching instructions using write instruction, and this process manually will process and execute the instruction as it should be. Then we write the rest of the instruction in place where it should be. Then we replace that by the beginning of our instruction, and in fact, in any case, we might call first
сначала, если мы пойдем на этот треп, если мы еще не успеем,
if we go to that thread, we might have operator's exception and processor exception. If we want to replace the instruction, this code, we have either to process it quite well. Okay. Thank you for the presentation. My question concerning performance. Did you give any assessment of the performance gain that can be attained when on critical routes when you use static branches versus common branches that are generated by compiler without such optimization in your architecture? First, that depends on the place where you are using it. If it is used in the place where we previously had check of global variable, if that variable was always removed from the cache, the address to that variable will take a lot of text, one text to check the instruction, and then for the lower cache and so on. In this case, we considered the productivity, not only of the work, but also the productivity of implementation of the new code. Implementation of static branches will make it possible to give some systems,
because potentially they could deteriorate the productivity of the code, its performance.
Sorry. Just a moment. Please take this one.
Well, so what would be in those clock rates in the architectures, to assess our overhead costs? We are talking about in reswitching, yes, when we make the reswitch. As to clock rate, I don't know exactly, but in the implementation which I have now, what do we have to do? First, we've written it, we've written this instruction down. We made flash 1 or 2 strings on cache. Does take a lot of time. Everything which takes up a lot of time actually, because we evoked invalidation using inter-kernel disruptions. So more time will be needed for that, because we sent this disruption to all the kernels. Invalidation will not take a lot of time as well. It's about marking 2 strings to put a flag invalid, which could be done over several instructions. Major problem in the implementation was that actually we are launching inter-kernel disruptions for all processes. Microphone is not used. We don't flash the entire cache, but one string only, one line, whereby we've written this instruction. For us, it will be 64 bytes of data, not the entire huge hash which will flash. If we flash entire cache, it will be bad, because all the data will be washed out of cache, and as the flash, we flash a big number of different data in this tool. It will take some time, but in this particular case, it's just we've written just a couple of strings. It does take a lot of time. Microphone is not used.
Well, but not this time, I think. Please say thank you to the speaker. And I think that it's over. И я думаю, что на этом в этой секции мы с вами завершили работу.
We have finalized our work in this session. We have half an hour recess, then we'll have the final presentation just in another. Then we'll close the conference.